Hello, my name is Thomas Sillo from Acoustic Research and Design Limited, and I'm presenting today my reflections on the whole stage imaging for performing arts, and particularly a machine learning experimentation. Room acousticians are preoccupied with reflections of the sound emitted on the stage so that they reach the audience early and from a lateral direction. This is the essence of acoustic design for performing arts. The traditional approach is to start with a point source on the stage and conduct all array tracing to optimize the reflection coverage for all reflecting surfaces or reflectors. This needs to be repeated for all possible source positions on the 200 square meter stage, including the cello, the winds and the percussion, the violins, and the choir. With today's parametric tools, one can modify the curvature and optimize it and see in real time the reflection coverage. But it is only for this particular source position. The process needs to be repeated for another and another until we are confident the sound from the entire orchestra is supported and projected to the audience. When looking at this series of images, it becomes obvious that different stage sections involve different sections of the reflectors. So the plot thickens as one change to a continuous surface to optimize one stage area reflection may actually affect its performance for another stage area. The idea here now is to start from the receiver position rather than the source and see if the existing technology can help us optimize reflections for the whole stage. Using rendering engine available, one can show a much larger density of ray tracing. Reflectors become mirrors and the orchestra becomes a set of radiating lights. We can see that from a receiver position, a reflector provides a reflection for all instruments on the stage. The architect intuitively understands this image, and one can subjectively assess the effectiveness of the reflector while roaming amongst the audience. This is real-time video produced on a reasonably priced laptop. If the architect understands the image, then they also understand the purpose of the reflector and the effect of its geometry and position. For example, here's the effect of increasing the height on the strength of the reflection. The sound reflection gets weaker as the canopy height increases. Another example is the visualization on how multiple reflectors combine their effect. As here, when we had the walls on the side and the rear of the stage. The question is, can we quantify this effect? Or in other words, how much more red, blue, pink and purple? Now the tool exists and runs and has been used in collaboration with architects in the past, so this is fine. It's just how we can actually have a quick check once we're happy directly in Rhino on whether or not we are missing a little bit of one stage area. Let's start with a simple case of no reflector. A color threshold analysis returned the RGB color codes for all the pixels in the saved photo. This is well known. Technique of just image splitting the colors component. The RGB code can be thought as a coordinate in a 3D RGB space. 0, 0, 0 is black and the top maximum point 255, 255, 255 being white. And we can compare the two images and the two statistics of these images. If we could compare them and quantify them, we might be able to quantify the difference in these two images in a meaningful way. The points are spread in a 3D RGB space, and assigning to each point the nearest color is a slow and manual process. So first, we simplify the problem by excluding the original pixels from the result. For that, we operate an image difference and inversion. Until now comes the machine learning tool to look at all of these 9,920 by 1,440 pixels in a much faster way and try to assign them to the original colors from the orchestra, which are represented here in the 3D RGB space. First, we can delete the white, the gray, and the black as they carry no information. They are more or less a constant background. And then, using an unsupervised algorithm, we can find the cluster of points in the 3D space. Now, we decided on an unsupervised algorithm so that we could actually subdivide the stage into more smaller subdivisions and add a color without having to go back into the code and change the number of clusters. The k-means cluster number is higher than the number of input color assigned, so assigned to the orchestra to account for shadows and resolution effect as well. And finally, the 2.7-ish million data points are not relevant anymore, and they can be dumped from the memory as they only to keep the centroid and the associated cluster population count. What you see now is the centroids, the average points of all that population. For each one of these centroids is associated a population count, and that's what we are adding up. Now, this picture is done with a high number of clusters. Here how we got it. In Rhino we have control panels, and we can navigate in real time to select the locations that we want to assess. We can adjust the reflectors, their geometry, bend them until we're satisfied. Then we can click to save the image. It will start render the first one with reflectors. And then once this is done, we will get the reference image, which is the one without the reflector. This takes a few seconds and is not obviously in direct time. But once the images are processed through MATLAB, we get the cluster in the 3D RGB space. We also get, from that, the population. So we can import the data back in Rhino and actually plot the data any way we want. And here, just out of convenience, we've just plotted straight the spheres in the 3D space with the same origin. Once we have these, we are left with 4 numbers representing the images of the whole stage, because we had 4 zones. The 4 clusters and population counts can actually be plotted any way we want. We had shown the spheres in the 3D model. It could have been a plot in Excel or even a plot directly in the Rhino viewport. What we see is almost in real time the reflector's efficiency to serve the whole stage. And here's an example. When we add the canopy, we have even out the reflection coverage for all of the orchestras. As you can see, there's a more even distribution of the different stage areas as represented in the image. When we introduce more reflectors, like the side walls on the stage, we introduce more reflections. And we have to be careful because we might throw that balance off. The canopy was really efficient because it's simply symmetrical, sitting above all the orchestra. The side walls will have a reflection in a different plane with respect to the receiver. And so we might throw out that balance. For example, on this view, we have a second order reflection from the side wall to the canopy that actually provides more coverage for where the red zone of the orchestra, the violins, but not so much for the cellos. And if the viewer was looking at the stage from the opposite end of the room, on the left-hand side of the screen, then that balance would have been in favor of the blue zone of the stage. And this is as much work as we've managed to accomplish so far. In conclusion, we have developed a practical way to communicate with the architect and visualize sound reflections for the whole stage, one receiver at a time. It's a great tool of communication and it stands by itself. Our attempt at quantifying the coverage based on machine learning, color clustering, and also the renders produced is promising. It's fast and seems to work with low rendering pass numbers. Yet the implementation is limited by the communication between Rhino and MATLAB to this stage, and we expect that a Python or C# script embedded in Rhino will speed up the process. We also want to make sure that the data that comes back is related to the standard acoustic parameters that we might actually use in room acoustics. This will be for our future work development. Thank you.